Hey class, it's going to be your 7-5 recording. So in this one, we're finally going to solve some of these systems we've been setting up. So we've got our vector matrix system, x prime equals a times x. And since that looks a lot like our first order equation that looked something like that, which had solution x equals k e to the a t, we're going to try a solution that's similar to that. So we will try vector x equals a constant vector times e to some lambda t. So when we take that derivative, we get x prime equals lambda k e to the lambda t. And if we plug that back in to our system, we get lambda k e to the lambda t equals a k e to the lambda t. So e to the lambda t can't be 0, so we can divide by it and get lambda k equals a k. But this is precisely our eigenvalue problem. This is another reason why we called that the characteristic equation, the equation to find the eigenvalues, is because the lambdas that will work up here, so this will work for where lambda is an eigenvalue of a, and k is the associated eigenvector. So that will give us a solution to, or x prime equals ax. Let's do an example. So if we have the problem x prime equals 2, -1, 3, -2x, and we want to find the general solution. So a equals 2 minus 1, 3 minus 2. And we're looking for the eigenvalues. And remember, the eigenvalues are lambda, which are the solutions of the characteristic equation, determinant of a minus lambda I equals 0. That's our characteristic equation. So determinant of a minus lambda I is equal to 2 minus lambda, -1, 3, -2 minus lambda. So that's going to be equal to, let's see, 2 minus lambda times -2 minus lambda minus a -3, which is, when we simplify, going to be lambda squared minus 1. So lambda minus 1, lambda plus 1 equals 0. When lambda equals 1, if I plug that back into a minus lambda I times k equals 0, I get 2 minus 1, -1, 3, -2 minus 1. We're going to augment that with zeros. And this doesn't even row reduce, it's just directly equal to 1, -1, 3, -3, still augmented with zeros. These are dependent. That's always going to happen when you get an eigenvalue. So this tells me that k equals something like 1, 1. It's anything that is equal, where x1 is equal to x2, because we're going to have x1 minus x2 equals 0. So k equals 1, 1 works to go with lambda equals 1. So then let's find lambda, or figure out what happens with lambda 2. Sorry, I should have called that k1. So to find k2, we set lambda equal to negative 1. So that's lambda 2. We'll call that one lambda 1 while we're at it. So lambda 2 equals negative 1. So a minus lambda 2I times k2 must be equal to 0. So a minus lambda 2I is going to be, what was that? That's 2 minus lambda, so 2 plus 1, negative 1, and then 3, and then negative 2 plus 1. And we don't really have to augment with zeros because they're never going to change, so I'm going to start skipping that at this point. So this is 3, negative 1, 3, negative 1, which row reduces to 3, negative 1, 0, 0, which tells me that 3k1 minus k2 equals 0, so I can have something like k equals 1, 3, right? 3 times 1 minus 3 equals 0. So we have that lambda 1 equals 1 and k1 equals 1, 1. And we have lambda 2 equals negative 1 and k2 equals 1, 3. Are both eigenvalue eigenvector pairs for our A. But that means that, let's see, where'd page 1 go? Remember, x was equal to k e to the lambda t, where lambda was an eigenvalue and k was the eigenvector. So each of those pairs gives us a solution. So we have x1 equals e to the t times 1, 1. And we have x2 equals, I should have written that in the other order, 1, 3 times e to the minus t. Let me write that that way. 1, 1, e to the t. Now, we could, without too much hassle, take a Wronskian here. I think, well, I guess we will. Let's go ahead and do that real quick. So w equals, so from my x1, I get e to the t, I just multiply it out, and then that's a column vector. And from my x2, I get e to the minus t and 3e to the minus t. And so this Wronskian is going to be 3 minus 1, which is 2, which is not 0. So they form a fundamental set of solutions, which means that the general solution x is any linear combination of these. So c1 times 1, 1 e to the t plus c2 times 1, 3 e to the minus t. I didn't ask this as part of the initial question, but the original question also asked, what is the behavior? So what's the limit of x as t approaches infinity? And you can see that it is unbounded, right? As t goes to infinity, then based on the sign of c1, this is either going to go to positive or negative infinity in both the x and y coordinates. This solution here will go to 0, so it won't affect anything as t goes to infinity. But that solution will either go to infinity, infinity, or minus infinity, minus infinity. Let's see. Trajectories. So a trajectory of the system x prime equals really any ax, but we're sticking with this example 2, -1, 3, -2 x results when we choose specific constants. Oops. Specific constants. So in this case, say we chose C1 equals plus or minus 1 and C2 equals 0. Then what do our solutions look like? Well, C1, these are along the line where y equals x, or I should say where x1 equals x2. But so we either have the x1, x2 axis or the xy axis, your choice on how you want to think of it. And so when C1 is a positive 1, we have along the line y equals x. Our solutions all radiate out like that. So this is for C1 equals 1, C2 equals 0. If C1 is -1 and C2 is 0, then all our solutions go out this way. If instead we looked at C1 was 0, but C2 was plus or minus 1, well, C2 is on the line, let's see, how would we say that? X moves 1, or x1 moves over 1, and x2 moves up 3. So we'd be something like this, the line y equals 3x, except e to the negative t. So as t increases, we get closer to 0. So those are two trajectories, very simple trajectories for this system. Solutions, in this case, that are on lines. And that's really all you need to know from 7.5. If you can solve the system, and really all you're doing when you're solving the system is solving the eigenvalue problem. So just to refresh what we did there, we take the determinant of a minus lambda I, and we set it equal to 0, and that gives us our characteristic equation, a polynomial in lambda. That'll give us a number of eigenvalues, up to multiplicity anyway, that is equal to the number of rows in our matrix. For each one of those eigenvalues, we can find one or more eigenvectors. So this was the simple case where we had two different eigenvalues, so we get two different eigenvectors that go with them. In order to find those, we plug into a minus lambda I, and we row reduce until we reveal that our system is dependent, and use that to figure out our eigenvector, which should always have the little vector hat. We do that for each one, so we did it again for K2 here, and then we take, you will probably need to check the Wronskian in your homework. The truth is, if your eigenvectors, if you have a 2x2 system and your eigenvectors are not constant multiples of each other, your system is going to be just fine. As a matter of fact, so long as you have distinct eigenvalues, there is no issue with this. You should always then get distinct linearly independent eigenvectors. And in that case, a linear combination of those eigenvectors times e to your eigenvalue t will be your general solution. So that's really it for 7.5. Thanks, guys.